Hello everyone, today we are jumping into section 2.1 of the Logic Design Review. In this lesson, we are going to work through truth tables in several forms, and we will do examples for each one. I will show you a unique, systematic method to evaluate any truth table that will make the process feel easy. Then at the end of the video, there is a surprise that will help you read, learn, and evaluate truth tables extremely fast. Alright, so what are truth tables? Well, truth tables are a simple way of representing the behavior of a combinational circuit. A combinational circuit is simply a circuit whose output is a function of its inputs. For example, suppose that we have a circuit called circuit 0, and this circuit has three inputs, A, B, and C. Then suppose that it also has two outputs X and Y. Well, since there are only three inputs, that means that there are only 8 possible combinations of inputs that circuit 0 will ever receive. We place these input combinations on the left side of a table, as shown here. Then on the right side of the table, we can define the outputs we want the circuit to produce for each given input. For example, if we wanted X and Y to be 0 and 1 respectively when all inputs are 0, we would update the table like this. Now, what would we want the output to be when inputs A, B, and C are 0, 0, and 1, respectively? Well, if we want that case to produce an output of 0 for X and 1 for Y, then we would update the table like this. As you can see, the truth table is simply just a condensed way of describing the behavior of a combinational circuit. All combinational circuits can have their entire behavior defined in a table, so a truth table is pretty handy when visualizing small-scale circuits. Note that whenever you don't care what an output is, instead of randomly picking a 1 or 0, we choose to write an X. This is important since it makes evaluating the table easier later. So why do we even bother with truth tables? Well, when designing a simple circuit, there are always 3 steps. The first step is to define the behavior of the circuit in a truth table. The second step is to then apply an algorithm to that table to extract the Boolean expression that the table is encoding. Then the last step is to convert that Boolean expression into a schematic. With those 3 steps, you can design any simple circuit. In this video, we will only cover how to extract the Boolean expression for a given truth table. In the next video, we will go over how to draw the schematic of a Boolean expression. Now you might be wondering, what is a Boolean expression? Well, a Boolean expression is a compact equation that describes how an entire truth table works. Every output of a truth table has a Boolean expression, and from that expression you can determine what the output will be for any combination of inputs. Next video, we will explain how Boolean expressions work. Now it's time to learn how to convert any truth table into a Boolean expression. The important thing to understand is that this process always follows the same 3 steps, no matter how many inputs the table has. Those 3 steps are listed on the slide. First, we map the truth table into a K-map. Second, we group the 1s and X's in the largest, cleanest way possible. Third, we translate each group into a term, then combine the terms to get the final expression. To make this easy, we are going to learn each step first, across multiple table sizes. Then, once the pattern is clear, we will do full end-to-end examples for each table size. Now let's go over step 1. Step 1 is straightforward. All we do is create a K-map for each output column in the truth table. Below, you can see the standard K-maps for 2-input, 3-input, and 4-input truth tables. For a 2-variable K-map, we use this template to transfer the truth table values into the map. Then, for a 3-variable K-map, we use this template. And lastly, for a 4-variable K-map, we use this template. Now let's apply step 1 to a real table. As we go row by row, we just take the output value and drop it into the K-map square with the same input index. Index 00 maps here, so we write a 1. Index 11 maps here, so we write another 1. All remaining indices have an output of 0, so the rest of the K-map entries are 0. Now let's apply step 1 to another real table, this time for a 3-variable table. Index 000 maps here, so we write a 1. Index 001 maps here, so we write a 1. Index 010 maps here, so we write a 1. Index 110 maps here, so we write an X. Index 111 maps here, so we write a 1. All remaining indices have an output of 0, so the rest of the K-map entries are 0. Alright, now that step 1 has been discussed and you have seen a couple examples, let's jump into step 2. So, step 2 is where the simplification happens. The goal is to circle all of the original ones in a way that follows the 4 rules shown here. Note that technically, rules 1 and 2 are not required to get a correct expression, but they are what give you the most simplified expression. Also, you can never circle zeros, but you can include excess if it helps to satisfy the 4 conditions. Now let's look at a couple examples of step 2 for 2 variable K-maps. In example 1, the 2 ones are not adjacent, so we have to use 2 separate circles to cover them. In example 2, the 2 ones are adjacent, so we can circle them together as one group. Now let's look at a couple examples of step 2 for a 3 variable K-map. In example 1, we use the excess as don't cares to make the circles larger, which simplifies the final expression. Notice that one circle wraps around the top corners. This is completely allowed. In example 2, we group the adjacent ones together, and we include an X when it helps us form a larger valid group. Now let's look at 2 more examples of step 2 for a 3 variable K-map. In example 3, the ones on the far left and far right can be grouped with a wraparound circle, so we make one large circle that connect across the edges, and that is allowed. In example 4, we still try to make as few circles that are as large as possible, but here the one at index 111 is isolated, so it must be circled by itself, while the other ones can be grouped together. Now, let's look at a couple examples of step 2 for a 4 variable K-map. In example 1, we use wraparound grouping on the edges, so the corners can still be grouped even though they look separated. We also use the excess in the middle to form a larger group, which helps simplify the expression. In example 2, we form the largest groups possible again. We have a tall group on the left, a long group across the middle, and we use an X in the center to make that group larger. Now we can discuss step 3, where we turn each circle into a Boolean term. Each circle produces one term, and then we add all of the terms together to get the final expression. To do that, for each circle we make a small table. The top row lists the inputs in the same order as the original truth table. The bottom row lists the binary indices of the K-map squares that are inside that circle. Then from each table, we extract the term using 3 rules. If an input changes down its column, we drop that variable. If an input is all ones in its column, we keep the variable as normal. And if an input is all zeros in its column, we keep the inverted variable. Now let's apply step 3 to this 3 variable example. Each circle becomes one Boolean term, so we handle the green, orange, and purple circles one at a time. For each circle, we list the input indices that are inside it. Then we look down each column. If a variable changes, we drop it. If it stays 1, we keep it. And if it stays 0, we keep it inverted. From that, the green circle gives this, the orange circle gives this, and the purple circle gives this. Then from those 3 terms, we combine them to get the following expression. Also notice that when we drop a variable, it does not disappear into nothing. It effectively becomes a 1, since it is no longer affecting the product term. In this example, I left those ones written out just to make that point clear. Normally, you would not write them at all, and you will see that in the next example. Now let's do the same thing for a 4 variable example. Just like before, each circle produces one Boolean term, so we handle the green circle first, and then the pink circle. For each circle, we list the input indices that are inside it, then we scan each column. If a variable changes, we drop it. If it stays 1, we keep it. And if it stays 0, we keep it inverted. For the green circle, B and D are the only variables that stay constant, so the term is BD. For the pink circle, B is always 0, and D is always 0, so the term is B prime D prime. Then we simply add the terms together. The final expression is BD plus B prime D prime. Let's now do our first complete, end-to-end example. In this example, we are going to extract the Boolean expression for the output G of this 3-variable truth table. If you are feeling ambitious, pause the video and try it yourself first, then come back and check your work. Step 1 is building the K-map. First, we label the K-map with the correct variable names so it matches the standard 3-variable template. Then we go row by row through the truth table and copy the G outputs into the matching K-map cells. Remember, X means don't care, so we copy the X into the K-map as well. Step 2 is grouping. Now we circle the ones, and we can include XS if they help us make larger circles. Here, the best simplification comes from making these two groups, as shown. Step 3 is generating the expression. For each circle, we list the indices inside it, then we look down each variable column. If a variable changes, we drop it. If it stays 1, we keep it. If it stays 0, we keep the inverted version. Finally, we add the terms together to get the Boolean expression for G, shown here. Let's now go over one more complete example, this time with a 4-variable truth table. This one is taken directly from the textbook. If you want to master this quickly, the textbook is a great supplement to these videos because it includes many more fully worked examples, practice problems with complete solutions, and additional assignments with full solution sets. One quick note before we start. The index column in this example is written in decimal instead of unsigned binary. That is just a cosmetic choice. It does not change the process at all. So, to start, step 1 is to map the Z column into the 4-variable K-map, as shown. Step 2 is to circle the ones using the grouping rules, which gives us these 3 circles, including the wraparound group on the right. Step 3 is to generate one term per circle and add them together, which gives the following expression for Z. Now it's time to reveal the surprise I mentioned at the start. Well, the surprise is that since the 3 steps required to solve K-maps are deterministic, a computer program can automate any K-map problem. Because of this, there are many free online calculators that let you enter the table entries and instantly get the Boolean expression, and sometimes even the schematic, for your truth table. What you're seeing right now is one of those websites. These sites are a great way to check your work, so I definitely recommend using them. That's all for now, and I hope to see you next time.